In the last chapter, you have learned how to display a quantitative variable with a histogram. In this chapter, you will learn how to display the same type of variable, a quantitative variable, with a 5-number summary and a box plot, which is a different way to do it. In order to provide the 5-number summary of a distribution, the first value you have to find is the median. The median is the number right in the middle of a distribution. It's the exact midpoint. If the number of observations is odd, if it's an odd number, the median is the actual number in the middle. And if the number of observations is even, the median is not an actual number of the distribution, but it's the mean of the middle two numbers. The next slides will illustrate this. Here's an example. I have a small data set of 11 observations. That's a distribution of numbers. These 11 numbers shows the number of goals player Mike Fisher scored during his 11 seasons with the Ottawa Senators. So each number represents the number of goals in a different season. Here in this data set, it's raw data. They are organized in chronological order. And the median here in this data set is 15. We're going to see why. Remember, the median is the exact midpoint of a distribution. So in order to find it, the very first step is to arrange the observations in ascending order from the smallest one to the largest one. This is what you can see on the slide. And the median is the exact midpoint. That's pretty easy to find when you have a very small data set as this one. But when you have a large data set of thousands of numbers, you cannot count and go see where the median is. So you have to use a very easy formula, which is n plus 1 divided by 2. N is the number of observations. So here I have 11 observations. 11 plus 1 gives you 12, divided by 2, 6. So the sixth number of the distribution will be the median. Here, the number 6 of the distribution is 15, so your median is 15. It's an actual number because you have an odd number of observations in the dataset. When the number of observations in your dataset is even, the median is not an actual number. It stands at the middle, at the center of two numbers. So it's the mean of the two central numbers of the distribution. Here I have 12 observations. I imagine Mike Fisher scored 30 goals during a hypothetical 12th season. So I have 12 observations, which is an even number. I use my formula. 12 plus 1, 13, divided by 2, 6.5. So my median will be exactly between my 6th and my 7th observation. So here the exact midpoint between 15 and 18 is 16.5. So my median in this dataset will be 16.5. It's not an actual number in the dataset because the number of observations is even. But it's exactly in the middle, at the center of the two middle observations. So you know how to find the median in a dataset. But knowing the median is not enough. It tells you where the center is, but it's the only thing it tells you. It doesn't tell you if the observations are really spread out around the middle or are very close to the middle. It doesn't tell you if the distribution is skewed left or right. So you need more numbers to describe a distribution. You need what we call quartiles. There are 3 quartiles in a distribution. The median, we have just seen, is the second quartile, Q2. The first quartile, Q1, is between the smallest observation and the median. So it's the number located at the first quarter of a distribution. 1/4 of the observations are smaller than Q1, and 3/4 of the observations are bigger than Q1. The third quartile is located at in such a way that 3/4 of the observations are smaller than Q3, and 1/4 of the observations are bigger than Q3. You will practice that in the next slides. How we find quartiles is different depending on if the number of observations is even or odd. Let's start with a dataset with an odd number of observations. It's the same dataset we have previously used here. So we have 11 observations. The median, or Q2, second quartile, is 15. We do not use 15 in order to calculate Q1 and Q3. We erase it because it's an actual number of the distribution. So in order to calculate Q1, you will only use the smallest half of observations, here from 4 to 13, and you will not use 15. So which number is exactly at the center of the smaller observations? It's 7. So 7, or Q1, is actually the median of the smaller observations when you do not include Q2. To find Q3, you proceed exactly in the same way. You take the largest half from 18 to 25. You do not include the median in your calculation, and you do find the exact midpoint of this larger half, which here is 22. So you have found Q1, the first quartile, and Q3, the third quartile, in your data set here, which is composed of an odd number of observations. We proceed in a different way when the number of observations is even in the dataset. So here I have my same dataset with a 12th number, 30. So the number of observations is 12 here. It's an even number. Remember, when I have an even number of observations, my Q2, my median, is not an actual number. The midpoint here is between the two central observations. So here, remember, my Q2, my median, was 16.5, right in the middle between 18 and 15. When it's the case, when I do not use an actual number of my distribution for my median, I use all the numbers, including the two central ones, to calculate my quartiles Q1 and Q3. So here, to calculate Q1, I will use number 15. Q1 is the midpoint of the lower half of observations. So the midpoint here between my observations that go from 4 to 15. Here, the exact midpoint is located between 7 and 9. It is 8. I proceed the same way for Q3 for my third quartile. It's the exact midpoint of the bigger half of my observations between 18 and 30. So here it is 22.5, right in the middle. Remember, Q1 is the median of the smaller observations, the smaller half, and Q3 would be the median of the larger half, the larger observations. So, in order to have our 5-number summary completely, we only need now the maximum and the minimum, which are very easy to find. So, in a distribution, when I want the 5-number summary, I use the following values: the minimum, the first quartile, which is Q1, the median, the third quartile, which is Q3, and the maximum. We will see another example with another data set here. I have the same type of data set. It's another hockey player, Alfredsson, who played 17 seasons with the Senators. And the data set you see here describes how many goals he has scored during the 17 seasons. The numbers are arranged in chronological order here. If I want to find my 5-number summary, the first step is to put the observations in ascending order. This is what you can see here on the second line. The observations go from the minimum of 10 goals to the maximum of 43 goals. I have 17 observations. It's an odd number, so the median will be an actual number in my distribution. I will use my formula, n plus 1 divided by 2. I have 17 observations. 17 plus 1, 18, divided by 2, 9. So my 9th observation will be my median. It's 24. If I want to find my first quartile, it will be the median of my smallest half. I will not use 24 in my calculation because it's an actual number, the median. I will use the remaining numbers in the smaller half. I have 1, 2, 3, 4, 5, 6, 7, 8 numbers. The median will be exactly in the middle of these 8 smaller numbers here, right between 17 and 20. It's 18.5. So Q1 here is 18.5. I will do the same thing to find Q3. I will find the midpoint between the numbers of my largest observations from 26 to 43. So my middle point here is between 29 and 32. It's exactly 30.5. So here my 5-number summary will be 10, 18.5, 24, 30.5, and 43. When I have my 5-number summary, I'm able to draw a box plot, which is the way to illustrate it in a graph. This is an example of a box plot in this image. You see it's arranged vertically rather than horizontally. Sometimes you see horizontal box plots, but generally they're vertical. You have a central box, the green box here, which represents the median and the quartiles, and you'd have 2 lines extending from the box that go from the minimum to the maximum. And on the left, you see your scale here. So if I want to do a box plot for the number of goals of Daniel Alfredsson, the distribution goes from 10 to 43. My scale could be divided from 0 to 50, for example. This is how a box plot looks like. In order to draw a box plot, you will first have to find the 5-number summary of a distribution. Then draw small horizontal lines at Q1 and Q3. Then you join these lines to create a central box. You draw another horizontal line where the median is. And then you draw the kind of whiskers that extend from the box, that go from the box to the lower, the minimum, and from the box up to the maximum. And this is an example of a box plot. The one you see here on the drawing is very symmetric, but they're not always symmetric. Box plots are very good ways to describe and to illustrate skewed distributions. There is another very, very important notion about distributions, and this notion is called standard deviation. When you have a distribution of numbers, you always have a mean. The mean is what we call in our daily lives the average. But the true word in stats to describe the average is mean. So you know what the mean is. It's the sum of observations divided by the number of observations. The standard deviation goes with the mean. The standard deviation measures the average distance from the mean. For example, if I give a test in my class and I find out that the mean, the average, the mean score is 80%. Students have all sorts of different scores. Some of them do have 80%, right at the mean, but not all of them. Some of them have below the mean, 65%, 40%, 78%, etc. And some are above the mean. They will have 90%, 85, 99. So whatever your score is, you're rarely right at the mean. You're most often above or below the mean. And you can be very close to the mean, 78%, but you can be very far from the mean, far below the mean, or far above the mean. So the average of all these distances from the mean will be the standard deviation. If all my students score very close to the mean, all of them have between 78% and 82%, I will have a very low standard deviation because there is not a lot of variation in my class. But if students have any score between 10% and 100%, I have a large standard deviation, have a lot of variation in the grades of my class. This is another example. Suppose that in my street, I have two houses. The first house is occupied by two parents and two little children. The parents are 38 years old, both of them. And one child is 1 year old, one child is 3 years old. The average age in this house, the mean, is 20 years old. But all members of the family are way above the mean or way below the mean. They're far from the mean. So there is a high standard deviation in this house. In another house, I have 4 students renting. One of them is 20 years old, the other one is 22, the other one is 18, and the last one is 20 years old. I have the same average age in this house, 20 years old. The mean is 20. But I have a very small standard deviation. It's low because everyone is very close to the mean. You will probably never have to calculate a standard deviation by hand in your life, or yes, maybe in a test this year, but it will probably be the last time because a software will do it for you. But it's good you know how to do it. First, you have to consider all of your observations. Here, the left column shows 5 different observations in a distribution, 3, 6, 9, 5, and 2. This is your first step. You write your observations. The best way to do it is to do it the vertical way like this, and you find the mean. The mean here, the average, is 5. 3 plus 6 plus 9 plus 5 plus 2 gives you 25. You divide by the number of observations, which is 5. It gives you 5. So I have 5 observations, and the mean is 5. I have to find the distance from the mean for each of these observations. So here, 3 is 2 below the mean. So the distance is 2. I don't care if it's above or below, because anyways, we're going to square these numbers. My second observation is 6, so it's 1 above the mean. Distance is 1. Third observation is 9. This is 4 above the mean. The next observation is 5. It's right at the mean. There's 0 distance. And the last observation is 2. It's 3 below the mean. Distance is 3. Then you have to square each distance from the mean. So here, 2 times 2, 4. 1 times 1, 1. 4 times 4, 16. 0 squared is 0. And 3 squared is 9. So I have here my 5 distances squared. And I sum it up. So here, 4 plus 1 plus 16 plus 0 plus 9 gives me 30. The next step is to take that sum and to divide it by the number of observations minus 1. So here, 30 divided by n minus 1, I have 5 observations. So it's 30 divided by 5 minus 1, 30 divided by 4. It gives me 7.5. This number I just got, 7.5, is called the variance. And the standard deviation is the square root of the variance. So here the square root of 7.5 is 2.7. In this data set of 5 observations, the standard deviation is 2.7. So 2.7 is the average distance from the mean.